Hello and welcome everybody. Thank you for joining me today. I'm Francesco Zoffoli and we are gonna see how to use dependency injection to write maintainable software. Before we start, let's talk a bit about my background. I'm a software engineer building monitoring systems at Meta. I'm passionate about C++ and I use it throughout my career. I'm the author of the book C++ Fundamentals published by Pact, and in general I like writing and talking about C++. And before we start, let's have a couple of disclaimers. What we're going to talk about is difficult to get hard data. It's mostly based on my experience and practices I see used in the industry. I'm going to share a bunch of tools, techniques and suggestions, but it's up to you to decide which one and when to use it. And as usual, context is always relevant. Different constraints call for different solutions. So don't feel like you must follow these as rules. Is it an option that you have? But I believe this is a good starting point to write good software. And if you don't have a good idea of which approach to follow already, this can be a good path to start on. So what we are going to talk about today? We are going to look a bit about dependency injection and what it is. Then we are going to see what are the types of dependencies, how we can pass dependencies around, and finally we are going to see how we can abstract components. So what is dependency injection? Let's look a bit at the software that we work with. Likely it's composed by multiple components and these components interact with each other. A component should interact with another through an interface. What do we mean with an interface? An interface is a clear contract which has preconditions, which is what must be true at the time in which you call the implementation, and post conditions, which is what must be true after the call returns. An implementation might have other observable behaviors. For example, when you call a function, this might log into the standard out. But the user shouldn't rely on that because this is not what the interface is guaranteeing. And since there's an interface, there could be multiple implementations for the same interface. In this diagram that we have here, the interface is represented by the shape, and we see that the user is taking a shape, and then we have two implementations which are both offer the same shape. So which shape should the user component use? The core idea of dependency injection is that the component shouldn't care which implementation is provided to it, as long as it matches the interface that it expects. But how can we write components which work in this way? The idea is that we inject the implementation into the user. So we have various implementations, or even a single one, which implements an interface, and the user expects this interface. And some higher level code is going to decide which implementation to provide to the user. This last part about the higher level decision sometimes can be automated with libraries. But we are not going to see this today. We are going to just see dependency injection, how you would do it by manually propagating your dependencies. And the core point then is that you never want to instantiate your own dependencies. The dependencies should be passed as a parameter. The reason is that to instantiate an object, you need to know the concrete type. And if you know the concrete type, now you're not talking about the interface anymore, but about concrete objects. And if we follow the pattern defined by the dependency injection, we are going to end up with something similar to this picture. When we have a component which implements an interface and also uses another interface to implement this functionality, and then it has a bunch of implementation code. And various components depend on each other. And as we were saying earlier, there's a higher level part in this picture is called the main, which decides which component to instantiate and does all the wiring of the various components. The big win of dependency injection is that it's simple to validate the correctness of your component. because to validate whether B is correct, the only thing that you need to know is what is the contract on the interface that B implements and what is the contract on the interfaces that B depends on. Besides this, the code of B is going to be enough to evaluate whether B is respecting the interface that it implements. The other advantage is this makes it also simple to decouple components and makes testing easier because, again, we are working with interfaces and not with concrete components. So we talked a lot about dependencies, and we said that for dependency injection, you need to pass your dependencies as a parameter. And I'm sure all of you know how to pass parameters to function or classes. So what are we going to look at here? We are going to look a bit about how we can pass these dependencies around, because this actually has an impact on the design of the software. So how dependencies are passed around imposes constraints on the user of the interface and on the component which implements the interface. Let's see an example. Here we have a function which takes a shared pointer of a dependency. And what the shared pointer means is that the implementer of the function now knows that it can store, for example, this shared pointer for later use, because the lifetime of the dependency is going to be preserved. But on the contrary, the user of foo, so who calls foo, now need to provide a shared pointer. And potentially they might not have a shared pointer. In that case, they will need to allocate the object into memory to create the shared pointer. On the opposite side, there's bar, which takes a dependency as a reference. What this means is that the implementer of bar now has no guarantee about the lifetime of the dependency, except that, of course, it's going to be alive for the duration of the call. So, for example, if you needed to store it, it couldn't. But on the contrary, for the user, they just need to pass dependency. It doesn't matter whether they add a shared pointer, they add it on the stack, this is a constant somewhere, like a static variable somewhere. So there's more freedom on the user and more constraints on the implementer. And the thing to keep in mind when passing dependencies around is that you need to impose all of the required constraints for your implementation and only your required constraint. You don't want to over constrain your function, because you're going to put burden on the user without getting an advantage for it. And one of the things that we are going to see is about the method for lifetime management of the dependency, where I'm going to show how taking the dependency as reference can actually make the code simpler and give more options to the user compared to the typical approach of passing smart pointers. And the reason for this is that the component which instantiates the dependency is responsible for the lifetime of the dependency. And the same component can also be responsible then for the lifetime of the transitive dependencies of what we built. So we are going to see later on concrete examples on how this works in practice. So let's jump into the type of dependencies. And when we are talking about dependencies, we can roughly categorize them into big groups. One is a data dependency, and this is a dependency on some kind of information. And the other one is a behavior dependency, which is a dependency on some kind of action. For data, we want data to always be read-only. This is important because we want to avoid action at a distance. What is action at a distance? Let's say we have two components which access the same global variable, or even just a local variable which is passed to the two components. And these are passed as references. Now component 2 can modify this variable, and component 1 can read this variable. And what happened is that we, in fact, coupled the two components, because now component 1 can see the behavior of component 2. And this makes it very hard to evolve the two components. And it's actually very hard to reason about as well, because to know whether that component 1 has a hidden dependency on component 2 and vice versa, you need to look at the global code about everything that's shared. The moment the data is constant, this kind of coupling cannot appear, and it guarantees the independence of the components unless they have an explicit dependency between things. So data is mostly of two natures. One is constant, and one is data which might change over time. And see again that these are constraints. One is a constraint which is imposed on the interface. So the data that might change forces the interface to write code which is able to handle data which changes. While the other one is a constraint on the user. Because the data must be constant, the user cannot modify this data for the duration of the dependency. The other aspect of data as a dependency is that the shape of the data is the interface. This means that, for example, if you have a sequence of items, then this is the interface of the data. The other is that we want to use value types. So basically types which are represented by their value. An example is an integer, a string, right? Like if you have a string foo and the string foo, these two are functionally the same thing. This is just data. We don't want to have differences depending on the instance of the object. And the other thing is that it's better to make the shape explicit. So what this means is using structure type, the vectors, structs, or schematized types. An example can be protobuf or thrift or any of the schema option which can generate types to interact with these types. And the important part is that by looking at the type, you need to be able to know what you can get out of this data. So for example, JSON, it's generally best avoided, because when you get a JSON, or for example, a map of strings to strings, or a dynamic, an any, the user cannot look at the type and say, okay, I know I can access the key foo, right? You need to know what is inside there separately. And this makes the interface less explicit. So let's look what we're talking about. The shape is the interface. So let's say we wanted to get a sequence of items. One option for our function is to take this sequence of items as a concrete type. For example, a vector. This gives us the maximum performance, assuming, for example, that the user has a vector, and but it limits the freedom for the caller. Why? Because if the callers as a vector, this is just going to work with our function which takes a vector. But in the case the user has an array, we will need to convert it to a vector. And same if you have a set, it needs to be converted into a vector. If on the other case we use a view object, for example stdspan, performance-wise, it's still comparable with the vector, so very, very high. But the freedom for the caller is a bit higher. In this case, we can get sequences which are continuous. So for example, if you have a vector, it's going to work with span, and if you have an array, it's going to work with span. But again, in the case of the set, when we try to pass it to the span, this is not going to work. And the last option is to get a polymorphic object. For example, any range. Any range is available in Boost, is available in the ranges v3 library. And performance-wise, this is the one which comes at the most cost, at the highest cost, but it gives the most freedom to the caller, because in this case we are really representing any sequence of data, and it works with vector, with array, and with set. So in general, there's a common theme that you can go from the most generic solution, which works with in the most cases and has the highest cost, to the more specialized solution, which has the lowest cost. The thing to keep in mind is a bit also how this thing compose. So let's say we want a sequence of sequences. In the case of a vector, this can work because a vector of vector is compatible, of course, with a vector of vector. And similarly, a range of range can take as an input a vector of vector. Where this breaks is with span. A span of spans cannot take a vector of vector. We will need to create a vector of spans. So as from the practical point of view, what I would normally recommend is just to use the concrete type. Very often there's some type which makes sense. In general, in many situations, the conversion is not that expensive, but it depends a bit on the use cases. The other option that we haven't talked about here is to use a template. The moment you use a template, in that case, any type is going to be compatible as long as it has the correct interface, and the performance behavior is going to depend on the specific implementation of the type. So for example, whether you pass a vector or you pass a list, you're clearly going to get different performances, but that is in control of the caller. So let's look at data that is constant. When we want to pass data that is constant, we want to pass it as a const reference. With const reference, it means that the implementation is not going to modify the data. What we also need is that the caller must not modify the data, because first, it's surprising when a const reference changes. So for example, you access the IDs in the code here, and then you do an operation, and then you modify the IDs again, and now the IDs are different. This is typically surprising. And the second reason is that actually it's undefined behavior if it's done by different threads. So the only way to do it safely, it will be through some kind of loops in callbacks, which make the code quite complicated. Unfortunately, in C++, there isn't a way to say, pass me a reference which you are not going to modify. But this is a constraint that it's quite easy to follow. For example, if you declare your variables are const, this is just gonna work. And the use case for passing data as a const, it's for example when you have hard-coded parameters, timeouts when you're making calls, or parameters from a CLI flag. So you read the CLI flags at the start of the program, and then these are not going to be changing for the rest of the program, so you pass them as a constant. And in general should be the preferred way, and it's a very common way of passing data informations as dependency. The other kind of data is the data that might change. Data that might change is still read-only. It doesn't mean that our component can change the data. Our component never changes the data. This is a dependency. It's just accessing the data, and this data can change. When your implementation supports data which might change, it's important to make it clear. What you can do is using an atomic ref, for example. This comes at the cost. There are some limitation on the types that it can be used with, and also copies the type for x-axis. Another option is using a fully synchronized. This is a pair of lock and data, which guarantees that the lock is taken for every access to the data. And in this case, it's a general solution which works very well, but we need to be careful with this contention. There's the risk of contention. And this can happen when, for example, there are two components depending on the same mutable data, and one component takes a read lock and keeps it for a long time. When something wants to change the data because the reality of this data changed and tries to acquire a write lock, this write lock is going to be blocked until the read lock of the component is done. If after this, the second component tries to access the read lock, depending on the implementation of the lock, it might get the lock or it might block, but in any case, it's not going to see the updated version of the data, even if logically his check happened after the new data was ready. Another option to solve this problem is to use Folly Observer. This doesn't lock the data when accessing or writing and exposes snapshots of the data, so decoupling the contention, but comes with a higher cost as it stores multiple versions of the same data. The advantage of using data that might change with these classes is that it makes it easy to test. So for example, you can just pass a wrap value to the test, compared, for example, with having to mock whatever was producing the data. And the other advantages makes changing the source of the data trivial, because the component is just accessing this data, but it doesn't have any information about how this data is produced or changed. Changing the producer, which is whatever sets the value of this data, becomes completely independent from the consumer and make it very easy to change later on. The use case for data which might change is pushing behavior. So for example, when there's some configuration that changes, or for example, you want to reload data from a source, or if you have information on the file system that you're listening to, and then when they get changed, they get pushed to the component. For pool, a behavior is often the best solution, as it's on demand and guarantees freshness. So let's look at behaviors. A behavior can be, for example, a stateful effect, like scheduling operations, sending a request to a service, but it can also be getting data on demand, like accessing local state or fetching from a DB. Or even differently, it could be performing a pure computation. So for example, you have a complicated rule set, a set of rules that you need to apply to perform some action, and you want to abstract away these complicated rules from the component which performs the computation. And when we are talking about behaviors, we might be talking about single actions or bundle of actions. In the case we are talking about single action and we want runtime polymorphism, we can just use an std function or an std function ref. Let's see an example. Here we have a function which needs to get the configuration for a specific path. And we can see that we define our configuration loader as a function which returns the config and takes the config path, and then we just pass the function to our do stuff, our component. And when we call the component, we can just pass the lambda, which takes the path and does the load. Or we could pass the address of a function that we set up somewhere. In the case we want to have compile time polymorphism, we can use the concept. And to use the concept, we can use invocable and invoke result. And this can be done. I'm not going to go into the details of how concepts work. There are other talks which explain how concepts work, and I highly recommend. But in general, we can make sure that our type, it's invocable, can be invoked with an object of type config path. Let me get the pointer actually. Okay, our object can be invoked with a config path, and the result of calling with the config path is going to be a config. And this guarantees we can then take a template. This is an inline template with auto, which is constrained by the config loader. So it's going to take any function which is going to match that concept. Let's look at bundles. So bundles are a set of actions that we want to do as a unit. An example, for example, when we are talking about a runtime polymorphism, is to have an abstract base class, like what we generally would call an interface, when we have multiple functions into the same class. It's very important when using abstract base class to avoid having a concrete base class. The reason is that any data member that you put into the base class and any constructor is gonna run when anytime a derived class is gonna be instantiated. So for example, if you put logic or data inside your base class, even when you're going to instantiate a mock in the test, this data and this logic is going to run. It makes it very complicated to then do testing, especially if there's any kind of side effect happening in those situations. So just stick to having an abstract base class and derive from that. In the case we want to use static polymorphism, again, concepts are the solution. We can specify the methods that we expect on the type and what is expected to return. The good thing is that when we want to mock the concept, we can just use our typical mocking strategy that we would use for runtime polymorphism. In this case, I'm using as an example Google Mock, and we can validate that our mock sender, and notice that is actually not implementing any interface, satisfies the iSender. So we actually get both behaviors with the same library without having to learn anything new. So this is a summary of what we just talked about when you want to do behaviors, how to pass behaviors. If it's a single action and you want runtime polymorphism, you can do std function or std function ref. If you have a bundle of actions and again you want to do runtime polymorphism, you can use an abstract base class. And in the case of static polymorphism, you can always use concepts, although in two slightly different ways. Sometimes behaviors are optional, so you want to make your dependency optional. When possible, I would suggest to try and make them not optional. If you can provide a no-hop or a default behavior for your dependency, it helps to not have this optionality. And the reason is that you avoid branches in the implementation, and it's just more streamlined. People don't have to guess, is this needed, it's not needed, what happens when it's needed. You just pass the default or the no-op implementation, and it's just more linear in the implementation. The other cases in which you actually want to pass, you need an optional dependency. You can use std optional when we are talking about single actions. So for example, an std optional of a function, or you can use observer pointer or an optional reference wrapper of the type. Optional reference wrapper is quite ugly to see, and people would suggest, hey, that's exactly the same thing as a pointer. But the pointer actually comes with a bit of an overload of information. Sometimes people are going to be questioning, does this take ownership? Can it be, do I have to free it at the end? And to avoid all of these questions, like having the optional reference wrapper, it actually just makes it clear. When internally in your implementation, once you get the optional, you can change this to a pointer, because you're going to know that this pointer is just accessing the object and it's not actually owning the data. When we're talking about dependency, the other thing to talk about is that it's better to pass data as dependencies rather than a behavior. And the reason is that data is less powerful, so it's easier to understand. So if you have an example here, when foo is a function which calls some function and get data, you can imagine this as being a dependency. And once we get the data, we do some stuff with it, and then we call another function, for example, a callback with this data. This can be changed from the previous example to this one, where we take the data as an argument, we do stuff, and then we return the data to the caller. This is easier to test. It's easier to compose, because once we have the data, for example, we can call different functions with this data. We are not forcing to only call whatever was specified in the initial function. And when you're reading the code, there's less of a jumping from one place to the other because even in the execution stack, it's gonna be flatter, so you don't have to jump in as much. It's clearly important that this do stuff with data is actually a bit meaty. There's a bit of logic, interesting logic going on there, because when we change a function to be like this, At a higher level, there's going to be some other function which gets the data, passes it to this function, and then with the return data does something. So if the do stuff with data is very little, we are going to end up with something which looks very similar to this anyway. All right, so we talked about how we can take the dependencies, and now we can talk about how we can pass the dependencies to the various components. So we have two options. We can pass the dependencies to the constructor, or we can pass the dependency as an argument to a function. The important thing is to not use setters. The setters enable cycle, they confuse lifetime, they force to handle the case in which the dependency is not set, they force to handle the case in which the dependency changes at runtime. Let's see an example. So we have component A, and then we have component B, and then we set the dependency of component in A to B. But then at this point, you might question, what happens if component A accesses the dependency in its destructor? We would access a dangling reference to the component B. And then we have component B, which set the dependency on A. And at this point, we have a cycle, and changing this becomes very hard. So much better to avoid having setters. So let's see an example of how we could be seeing the dependency passed in a code base that we might be working on. And here we have foo, which needs a logger, and it takes a path of where to log, and then instantiate a file storage, providing the path when this file is where the log is going to be stored. And then we create a structured logger, which takes the storage, and we set this as a logger. And then the class is going to use the logger. But to do this, foo needs to know that file storage requires a path, then the structured logger requires a file storage, and that the structure logger is an implementation of the iLogger. The other thing is that we are forcing the structure logger on taking the storage as a unique pointer. And this is there's a lot of coupling here, because this class didn't actually care about all of this implementation, they just wanted to get a logger. And the usage of the class is quite simple though. We can see that we just instantiate foo and we pass the parameter, which makes it appealing. But let's say what is the alternative with dependency injection. So with dependency injection, we just get the logger as a reference. We take it as an argument as well, because as we said, we are not specifying, we are not deciding inside the component about what is the dependency that we need to use. And we just set the dependency. And when we want to use, we want to instantiate, it's at the higher level that the decision about which logger to provide is made, in this case a structure logger, and the main needs to know about all of these dependencies. And the advantage of this is there's decoupling. So the foo doesn't need to know anything beside that it needs what is the contract with iLogger. And the other advantage is that changes to file storage have no impact on foo. So let's say that, for example, file storage needs a new parameter. In the previous example, the first example, we would need to get a new parameter inside foo to pass to the file storage. But in the second example, foo doesn't know anything about the file storage, and the main would change. The other advantage is that lifetime is automatic, although to be honest, also in the first one it was automatic using unique pointers, as long as everything is passed as a unique pointers. And the other advantage, which doesn't come with the unique pointer, is actually easy sharing. So imagine that you have the logger that you want to use in multiple classes, or you have a thread pool that you want to share across multiple classes. If you're passing dependencies as unique pointers, it becomes very hard to share the dependency around. And you might say that this is a bit of a straw man, because even in your code right now, you wouldn't be passing the string to the log, but you will pass the unique pointer to the logger. And in this case, we are still talking about dependency injection. It's just done by using unique pointer. We get the advantages of using dependency injection. but we are still using, we still have the constraint of being prevented from sharing the object around, and also it makes creating fixtures in test more complicated. Let me show you what I mean. So here again, I'm using Google Test to as an example, but the problem is similar in other testing framework. And in our fixture, which is instantiated for each test, we create our concrete class, and we want to pass down our dependency, which is a mock dependency. And once our test start, our mock dependency has been already moved into the class under test. So we cannot access the mock anymore to set the expectations. So the other option is actually to use a share pointer, and this works. It's actually an option which is used in many code bases, and there might not be big problems with that. It still forces the lifetime management to be a shared pointer. So let's, for example, imagine that you're working with some external library which has its own managed pointer instead of a shared pointer. You would need to either infect your code with this new managed pointer, and then changes later on become harder, or you might have to migrate, be able to translate from this managed pointer to a shared pointer, or even if you have pointers, sometimes classes have you get references to classes, but these classes are already managed by a shared pointer. So a lot of times you actually need to use the enable shared from this to get the original shared pointer and don't have problems with the logic. While on the other side, the references are universal. If you have an object, you're going to be able to have a reference from it. And as long as you manage the lifetime correctly of the reference, this is going to work very easily. The other thing to be careful about is about piping. So a piping is when you get some dependency just to pass it to another dependency. And the example is the string info, the logging path info, which we take it and we just pass it into another dependency. Instead, what we can do is pass this dependency directly before into the original dependency. So let's see an example here. An example of piping, here we are getting the config loader and the path, and then the only thing we do is pass the path to the loader. The alternative to avoid piping is to have our action, my action, take a function which just gets a config without any parameter, and when it wants to get the configuration, it just calls the loader. And the higher level function does the provides a function which calls the loader with the provided path. And we'll see something similar to this later as well, but this basically breaks the dependency between the specific of the configuration loader and the string. So for example, imagine that the path will change to be a path type. You wouldn't have to go and change the action because it never cared about the path, it only wanted to have the configuration. The other option to pass the dependencies is to pass them as function arguments. The use case for this is, for example, is when you have functions. The fact that we use dependency injection doesn't mean that everything needs to be a class. C++ supports functional first-class citizens in C++. They're very powerful, so use function freely. And when you need a dependency, you can simply inject it. And the other reason to use passing dependency as a function argument is when the caller of the function need to control the dependency instance. So for example, this instance might be changing every time that we are calling the function. And the other reason to do this is in case there's a limited lifetime for the dependency that we need to pass around. So we cannot pass it in a constructor because the lifetime of this dependency is shorter than the class that needs to take it as a constructor. So instead we pass it in the function. Let's see a concrete example for this. Let's say we want to have a functionality which formats a message for a user supporting internationalization. So we have our translator interface, which is a function which takes an untranslated message and then translates the message. And then we have a formatter, which formats various argument, which takes an iTranslator and returns the formatted message. The reason why we are passing the translator into the formatter is because the translator needs to know the language to which it needs to translate. And to get the language, we need to know the language of the user. So let's see concretely what this is. So we are going to start with instantiating our formatter, and our formatter is going to be used throughout the duration of the program. Later on, we start processing a specific user, and at this point we can get the language of the user. Since now we have the language, we can instantiate the translator for that specific language, and then we can call format with the translator for the specific user. But this is not the only option that we have when we are talking about injecting dependency. What is the other option? Another option is to change the translator to take the untranslated message and the language. And then the format, we pass the iTranslator to the constructor, so the formatter is only going to have access to a single translator. And then when we call format, we will pass the language of the user. And this is how we would look our stack. We first instantiate the translator, which is going to shared for the duration of the program. Then we pass it to the formatter. And later on, we start processing the user, we get the language, and at this point, we can call format. But if you notice, what we are doing here is that we are piping the information, the language, to the translator. The formatter doesn't care about the language. It only cares about translating a message into the correct language. And so let's see. And this is going to make harder because, for example, if you change the language, if you change what we need to translate stuff, we will need to go and change the formatter, which actually was independent from this. Let's see what is the other alternative to use the dependency injection to solve this problem. We are back to the example in which the translator takes an untranslated message and the formatter takes the iTranslator as a constructor parameter. So where's the language here? How can this work? And the reason is that we can change again the order in which we instantiate the dependencies. So in this case, we first start processing the user, at which point we can get the language. With the language, we can instantiate the translator for the specific language. Then we can pass it to the formatter. And then again, we can call format with all the information we used. So again, in this example, we saw how passing the dependency as part of the constructor or as part of the function can change the order. So for example, sometimes formatter was instantiated first, sometimes translator was instantiated first, and impacts the sharing that we can do. So in this example, we are going to use a single formatter for a single user. We cannot share across users. But in the previous example, we could share the formatter across multiple users. So again, what I wanted to show with this is that you have a lot of flexibility by using dependency injection to pass dependencies into the various classes. And what is the correct solution depends on the software that you are building. But the other thing to notice is that when I was talking about this example is we are going to instantiate the class. But we said that we don't want to instantiate classes because then it means that we are programming against the concrete type instead of the interface that we are working with. So for that, we can solve these using factories. So a factory fundamentally is still a dependency. It's just a function which from some parameter, it constructs a dependency. And factories are also dependencies. Everything that we talked about, so passing them as a constructor argument or passing them as a function argument, is still the same and applies in the same way for the factory. But when we define a factory, we need to define the abstract type which is returned by the factory, because a factory needs to return an interface, which is what the user is going to program about. And we cannot return the concrete type. So what can we return instead? Well, this is a bit of a lie, because when we are talking about static polymorphism, we can use concepts. And in this case, we can see how the concept is going to check that the result of invoking our function with the configuration path is going to give us back a type which satisfies the concept config like. And similar, when we call the function, we can assign it to auto. So this is going to be a concrete type, but which satisfies the constraint of the concept. But except for this case, what should we return? Well, we have an option. A typical option is actually to return a unique pointer. And this works when we are instantiating our dependency, for example, foo, inside the function. But how does it work when we want to have a dependency, for example, on some reference that we have already available? So this is also working because we can instantiate the class and pass the reference that we captured in the factory. But what is the case of, how does it work in the case you actually have another factory and you want to call this factory to get back a class that then you use? Here you cannot pass the pointer as the reference because you will get a dangling pointer. But if we just move bar, then we are passing a dependency, a unique pointer, and we saw that there's a disadvantage with this because of sharing. And as I talk about this, you're probably thinking, whoa, this is over-engineering. What are you doing? This is not something that happens normally. But actually, this is not very rare. Imagine, for example, that you have a buffered file reader that basically needs a buffer where to store the memory. And for this buffer, you actually want to provide it from some kind of allocator. So your allocator is going to be your buffer factory, which gives you back a buffer, and then you pass this buffer to the buffer reader. And you could say, well, the buffer reader should own the buffer because, for example, there's no point in sharing this buffer across multiple classes. But for example, it's not up to the control of the file reader to decide that the buffer needs to be freed after it's done using it. Maybe you want to reuse it. So it's not super common, but it's not very easy. It's not necessarily a very over-engineered problem. So, and we saw that in this case, we end up either having to manage dependencies as unique pointers or have dangling reference. So this is also a solution that doesn't work. Could we use a share pointer? Well, the share pointer has the same identical problem about what we talked about before. You get a share pointer and either you pass a reference if you're taking dependencies as references, or you're passing the whole share pointer and you're forcing everything to be managed with the share pointer. But the advantage of the share pointer is actually that it supports the aliasing constructor. So the aliasing constructor allow you to create a struct which holds by value the share pointer and foo. And in foo, we just pass the reference to the share pointer. Then we create a share pointer which holds the whole holder. And then we create another share pointer which stores the holder but exposes only the subset of the holder, which is foo, as ifoo. This is quite complex, but the good thing is that in the normal situations, like the cases that we saw before, when you don't have this dependency on factories, the usual approach for using share pointer works fine. And this more advanced approach can be used only when there are these more complex dependencies. The advantages of having a share pointer is that it's familiar, it's available, it operates well. A lot of libraries return share pointers or expect share pointers as dependency. The disadvantage is that it has a bunch of unneeded features. So for example, we don't need reference counting, we don't need the weak pointer, and also there's a dangling reference risk. Let me explain why. So in an example in which we have foo, which calls bar, and in bar we create a factory, which capture our A dependency, and then we call this factory inside bus. Now B provides a factory, could be capturing A. This means that if you take B and you store it in some other storage, for example, on a different thread, you might end up with a dangling reference, because it's not true that you can just, as long as B is alive, all its dependency is going to be alive. So there's a safe pattern that you can follow, which is that you take a shared pointer as in the dependency, you dereference it to get the reference, and from there on you forget that the shared pointer exists, because the shared pointer is guaranteed to be valid only for the duration, for the scope of your function. And this is quite similar to structured programming and structured concurrency, where this helps guarantee the lifetime of your dependency. But this is a drawback that having shared pointer provides. The alternative would be, for example, to design your own type, for example, an holder pointer, which guarantees that it's not copyable and it's not movable, and only provides the functionality that we need. Although I don't have experience with that, because in my code bases I always use the shared pointer, and to be honest, we haven't had problems with the lifetime of these dependencies. But this is something to be aware, especially because people need to know that you cannot just keep this pointer, putting it to a vector and access it later, because it's not necessarily valid. Another part of this is factories of factories. And again, you might be talking about, this is ridiculous, how is your ivory tower? But again, this is actually more common than it looks like. So for example, let's imagine that we have a connection that create a database. We have a company which have multiple databases depending on the enterprises that it offers the service with, and we have a connection to each different company, to each different database depending on the company. But our code doesn't necessarily care about which company we are connecting with. It just cares about having a connection to a database. So in this case, instead of passing the connection, the factory for the connection, we can just bind our factory with a specific company and get back a new factory which doesn't take the parameter and just returns the connection. This is conceptually very similar to currying. So where calling a function with the argument is like a sequence of calls of the function. And the advantage is that each piece of the logic is going to define the part of information that it knows. This is something which can happen, for example, with one level of indirection when one factory generates another factory. This is not rare. I only saw once when there's 2 levels, and I never saw 3. So if you're doing this a lot, start questioning whether your design is makes sense, because there might be overcomplications that it could be simplified. The other thing, and testing with factories, is that actually you can create a mock function and just return the std function to the factory, and then in your test you can set the expectation on the factory separately, so that you can control externally what this factory is going to return, even if it's been passed already into the dependency. So we talked about all of these components, but there's a lot of wiring that needs to happen to have these components work together. And the user might not know how to wire correctly these components, or they might not care about wiring these components all together. So how can we make this better for the user, and especially how we can create higher level abstraction for these components, so that we don't have to have these incredibly complicated 1,000 lines long mains just to wire all of these components around. We need to expose components which abstract over these sub-components. Let's see an example. In the image here, the round thing means an interface which is provided, and this half moon means that we are expecting an interface. And the different colors represent different kinds of interfaces. So we can see that here there's a macro component which is composed by smaller components, which offers an interface and expects two other interfaces. And inside there's a wiring of a bunch of different components which have different expectations, different interfaces to implement this logic. And from our point of view, we don't know what's inside A. A might also be recursively composed by smaller component and smaller components. And this component hierarchy allows us to create higher abstractions for our components so that our software can be more complicated by reasoning about higher level components that interact with each other without having to know the details of everything all the way to the smaller implementation. So how can we create these components? Well, one thing is the factory. We just saw how we can create a component which has a dependency on multiple other components. And the other option, though, is also, for example, to use a struct. And the reason for this is that a macro component, you can kind of see it as a new constructor for this component. So generally you don't need polymorphism. This thing is done inside, this component is created inside the factory or in the main. So it's fine to always return the same class. So in that case, we can use the same pattern as we saw before with the holder struct, but instead of putting into a share pointer and using the aliasing constructor, we can just return the holder struct directly. You see that our making function takes the two dependencies that our macro component has and then returns just the holder which is instantiated with the two dependencies. And this is how we will be creating our holder class. You would have the private section with all the internal components for that specific macro component. And then you would have a constructor which takes the interfaces that the macro component depends on. And then it does all the wiring inside here. It does all the wiring inside the constructor. And in the public section, it can have basically the component which exposes the interface. The other alternative actually is to also have the A component is in this example be inside the private section, and in the public part you would have just the interface reference which points to A. So assuming that there was an IA interface, you would here have IA reference which points to the A which is in the private section, and this is again could be set up by the constructor. For this to work, it requires the return value optimization and copy elision, but this is mandatory from C++ 17 anyway. The advantage of this approach is that it can expose multiple interfaces and can again makes the lifetime automatic, although as I said before, if you want to manage everything through share pointers, this also can work. And the disadvantage is that it doesn't support polymorphism, but generally we don't care for that thing. But more importantly, there's a physical dependency on the implementation details. So whoever calls this function is going to have to include all the headers of the internal implementation, which will not happen if you were returning the factory style with the abstract class. This is a great option for testability as well, because in the case, for example, everyone has probably shown a class where there's private methods which are actually made public because they are kinda isolated and they are complicated and people wanted to test that method specifically. What this gives the option to do is to actually split out this part of the implementation detail into its own interface and implementation put into, let's say, a private namespace. And then we can test the private implementation independently, and you can change your component to be basically a macro component of this in the implementation detail and then your logic. But from the point of view of the user, this is not going to matter. So the abstraction the component gives us a higher level components that can be composed, and also give us a new facility to split out the implementation and aid testing. So in conclusion, we saw an overview of what dependency injection is, how to define the interfaces for data and behavior, how to pass the dependencies between components, and how to defer decisions with factory. Finally, we also saw how to expose higher level components. And what I want to say is these are all tools. They are tools to manage complexity, but you need to be aware of it because evolving code, which takes parameterized dependencies, it's easier, but also it's more complex to understand. You also need to be careful when applying this concept because you want to make sure that the complexity that they introduce, they pay for itself. And then usually there's a trade-off between flexibility and understandability about the solutions that you take. I hope that the concepts presented here were useful and they will help you apply them to your code base to make your code simpler to work with. Thank you.